Welcome to lecture number 23. This will be the final lecture in our series. Our objective is to talk about generators in parallel, but before we do that, let's review the induction motor and the synchronous machine. And recall that a synchronous machine can be used as a motor or, in this particular case, a generator. An important aspect of the induction motor is the speed-torque relationship. A typical motor might look something like this, where this is speed, revolutions per minute, and this is torque. The operating point for a typical motor is here. We have a certain torque and a certain speed. We'll call this the speed of the rotor. And this point right here, where the torque drops to 0, we'll call the synchronous speed. We talked about slip, where slip is the synchronous speed minus the actual rotational speed divided by the synchronous speed. And we also mentioned that the synchronous speed was equal to 120 by the frequency, that's the electrical frequency at which the system operates, divided by the number of poles. Traditionally, we were limited by this equation. If the motor had 2 poles, it would spin at 3600 RPM. That's not quite true because 3600 RPM would be right here. The motor would actually spin at something less than that. If it was 4 poles, it would be 1800. Again, this dot here is the synchronous speed. The actual motor would be turning something less than that, perhaps 1750 as an example. 6 pole, 1200 RPM, 8 pole, 900, and so on and so forth. Moving forward, do remember this equation because it tells us that the synchronous speed moves in discrete steps depending on the number of poles. In this case, we had a 60 Hertz system, and we saw that we had these speeds available to us. Remember that in induction motor, there's always a certain amount of slip, so the actual RPM will be less than the synchronous RPM. For example, at full load, this 3600 synchronous might drop to 3525. This 1800 might drop to 1750. And so on. Also, keep in mind that this portion right here on our speed-torque curve is linear, and the speed of the induction motor is dependent on the actual load or on the torque that's pulled from the motor. When the load is light, it will be turning closer to synchronous RPM, and you'll see that the machine droops in speed as the load increases. Today's technology does change this a little bit. We have something called a variable frequency drive. On a one-line diagram, it looks something like this. You have the source. You have a box called the VFD. It takes in alternating current, and it outputs alternating current to drive the motor. At first glance, you look at this and say, well, that's fine. It's just AC to AC. But it's AC 60 Hertz on this side. But on this side, it will go from stall all the way up to 60 Hertz or even beyond if you want to. It is possible to overspeed the motors if necessary. You can also reverse the motor. And that's all under computer control in the VFD. Know that this variable frequency drive is very important and will be the subject of future classes. While we're here, let's work a typical problem that you might find associated with an induction motor. We are given 150 horsepower, a power factor of 90% inductive, an efficiency of 93%, and the fact that this motor operates on a 450 volt system. when you see numbers like this, there are a few assumptions you need to make. This horsepower is the output power as measured at the shaft of the motor. And this voltage, without any amplifying information, will be assumed to be three-phase, and it will be volts line to line. Our objective is to find the current, to find the complex current flowing in the system. As we get started, this is a 150 horsepower machine. We can convert that to watts. So 746 watts per horsepower gives us 112 kW. We know the efficiency is power out over power in. In this case, we're given an efficiency of 93. And that is our power out, so 112 kW, over power in. Power in is therefore 120 kW. That's 112 divided by 0.93. So there's 120 kW. Keep in mind that that's the total power of the machine. And at some point, we're going to want to convert this into a per phase. On a per phase basis, the power in per phase is a third of that. So that's 40 kW. We can then sketch our power triangle. So 40 kW on the base. And our power factor, theta, is equal to the arc cosine of 0.9. So arc cosine 0.9. So theta is equal to about 25.8 degrees. And back to our apparent power. Apparent power would be 40 divided by 0.9. which we can record here as 44.4 kVA. S is 44.4 kVA at a phase angle of 25.8 degrees. S is equal to VI complex conjugate. And we put all this together, so 44.4 kVA, 25.8 degrees is equal to the voltage, and our voltage was 450, so that's 450 divided by square root of 3 on a per phase basis. That comes down here as 260, and then I complex conjugate. So 44.4 at a phase angle of 25.8 multiplied by 1,000 divided by 260. The current is 170 amps at a phase angle of negative 25.8 degrees. Remembering that this was the complex conjugate. If we were to use a physical ammeter, the current on the line would be 170 amps. If this was the motor, and these were the lines entering that three-phase motor, each line would measure 170 amps. So if you put the meter here, it would read 170, here it would read 170, and here it would read 70, assuming it's a balanced system. And of course, the voltage phase to phase would be 450 volts. So 450 volts phase to phase. And once again, the line current as measured by an ammeter would be 170 amps. I won't go into it now, but do remember that the horsepower is equal to the torque in foot-pounds by the RPMs over 5252. And also remember that there is a power flow diagram where we have power in, power out, and power lost, including friction and windage, and things like I squared R losses in the coil. The last time we met, we talked about the synchronous machine. It was presented as either a generator or as a motor. As a generator, it was modeled something like this. You had the internally generated voltage, a winding resistance, and a winding reactance. So R and JX, with a current flowing in that direction. As a motor, it looked very similar. You have the reactance, the resistance, and the internally generated voltage. In the motor, the current flows this way. We have a terminal voltage on the generator. We have a terminal voltage on the motor. For both machines, we can make some KVL statements. The internally generated voltage is equal to the current by this resistance, R plus JX, plus the terminal voltage. So the summation of the voltages in a closed loop circuit is equal to 0. On this side, we would say the terminal voltage is equal to the current by R plus JX plus the internally generated voltage. And the only difference between a motor and a generator is which direction the current is flowing. In fact, in the last discussion, we connected the two together where we had serial number 1000, we had serial number 1001. One was used as a generator, the other is used as a motor, and we calculated the internally generated voltage from each machine. We could look at this another way by considering what happens in a locomotive. When we explore this locomotive, we see that there are multiple synchronous machines. There is a synchronous machine here called an alternator that's bolted directly to the diesel engine. There are also synchronous machines in the truck. It's called traction motor here, and in the back there's likely another traction motor as well. Again, those would all be synchronous machines. Now, when you think about the locomotive, consider this. When the locomotive is going up the hill, the diesel engine is working very hard and energy is flowing through the alternator, again, a synchronous machine, through the electronics to the traction motors, and up the machine goes. When the locomotive gets to the top of the hill and it starts to move down, the mechanisms shift. At that point, the traction motors become the generators. And while it would be really nice to convert that mechanical energy back into fuel, it doesn't work that way. What we do instead is we do this thing called dynamic braking. Turns out there's banks of resistors up here behind the cab, and all of that kinetic energy of the train going down the hill is turned into electrical energy in these traction motors, which again are synchronous machines operating as motors, and that energy is burned up in the resistors. The point of all this is to show that a synchronous machine may be used as either a motor or a generator. It all depends on the torque that's applied to the machine. In this case, the locomotive, when it's going uphill, the traction motors are indeed used as motors. When the train crests the hill and starts to go down, those traction motors are used as generators. The potential energy is converted into electric energy, and it's then burned in these resistors, known as dynamic braking. And that works very well for the locomotive. So instead of having mechanical brakes, which would wear out and get extraordinarily hot if you had a large hill that you were going down, instead you burn that energy in the resistors. And then you have, of course, large cooling fans to get rid of the heat. While we're here, we may as well work an example. In this example, everything to the right is a motor on a per phase basis. If we were to install a voltmeter here, we would be measuring the terminal voltage. PA stands for power analyzer, which tells us in this example that the terminal voltage is 277 volts at a phase angle of 0 degrees, and that the line current is 50 amps at a phase angle of negative 25 degrees. For this example, we want to find or calculate the internally generated voltage. Not much of a challenge in this particular example. It's just an application of Kirchhoff's voltage law. We say that 277 is equal to the current, so that's 50 amps, phase angle of negative 25 degrees, by this reactance, 0.1 plus J1, plus the internally generated voltage. That's 277 minus 50 at a phase angle of negative 25, and that's multiplied by 0.1 plus J. So our internally generated voltage is 255 volts at a phase angle of negative 9.8 degrees. Since we're here, we may as well calculate the power lost to that resistor, which isn't terribly difficult. So the power lost per phase is equal to the magnitude of the current squared by the resistance. In this case, it's 50 squared by 1. So that's 2,500 watts. So the power lost total, that's 50 times 50, that gives us the 2,500 times 3, because it's a three-phase machine. So the total power lost is 7.5 kW. The physical output of the machine on a per phase basis is the real part of the voltage, that's the internally generated voltage, multiplied by the current. So power out per phase, so that's 255 at a phase angle of negative 9.8 by 50 amps at a phase angle of negative 25. And we want the real part of that. So that's 10.5 kW. The total power is therefore 31.4 kW. We're going to multiply that by 746. Correction. We're going to divide by 746. So the power out is 42 horsepower. The efficiency is 31.4 over 31.4 plus 7.5. You read that as efficiency is power out over power out plus power lost, which gives us a horrible efficiency of about 81%, which means one of two things. Either this motor is working extraordinarily hard, or when I designed the problem, I chose those values poorly. You can take your pick. Moving on, let's talk about the synchronous machine. In this case, I mean the actual machine. There is a stator. There's a rotor. That rotor will have a certain number of poles. There will be an exciter. There may or may not be something called a permanent magnetic generator. When you put it all together, you end up with a machine that looks like this. As a sidebar, this document is from Cato Engineering, so named because it's from North Mankato, Minnesota. I used to live there. In fact, I lived in North Mankato, kitty corner to the actual factory that produces these machines. In the evenings, I would often go for walks around that industrial park. And I remember that the Cato factory was a little bit different. It was different because it made the ground shake. Every time you walked by, as soon as you got close to the factory, you could feel it in your feet. And what they were doing is they were stamping out these rotor and stator laminations. You see, these laminations are used to make the rotor. You see the rotor here, and here are all the steps to make the rotor. Those laminations are also used in the stator, and you see all the steps necessary to make the stator. And the rotor is the part that rotates, and the stator is the stationary part that does not move. Do remember that there's alternating current flowing in this machine, and we want laminations, we want thin sheets of steel to be separated by insulation so that you can reduce the eddy currents. Here's the rotor laminations. Rotor laminations are stacked together. Here you can see the core with the field windings. There's very thick wire wound around them. This is a 4-pole machine, so this magnet here, let's assume that's a north. This would be a south. The hidden magnet would be a north again, and then south here. So that's north, south, north, south. All of that is put together to make this mechanism here. Here's the field coil, like we mentioned. This here is the brushless exciter. Here's the PMG. Each of these shoes would be a magnet, so it'd be north, south, north, south, north, south, and so on. And the last thing on the end is the diode stack. To see how this all works together, you have to do a little three-dimensional thinking. So take the rotor here and insert it into the stator. And you can see that there is a correspondence between the length of the field coils and the length of the stator. To that assembly, we're going to bolt this piece on. So now this ends up surrounding this piece here. So we have a corresponding piece for the brushless exciter. In this two-dimensional drawing, we have the stator coil here and here. Again, that would actually be a complete circle. If you looked at it this way, you'd have the stator coils surrounding the field with the shaft there. You have a set of coils for the brushless exciter, and you have a set of coils for the PMG. To understand how this all goes together, you have to remember that the internally generated voltage of the machine is equal to K phi omega, where K is the machine constant, which describes the physical characteristics of the machine, how many poles, how the wires are connected together, how many wraps of wire there are, and so on. Phi is the B field, and omega is the rotational velocity. In this case, we want to really focus in on the B field, which is right here. So it's the strength of the B field that determines the output of the generator. The output of the generator is taken off the stator. That's where we're going to find the big, thick, heavy wires. In order to get the B field operational, we have to add energy somehow. We could use slip rings and have a physical connection, or we could use the brushless exciter. The way the brushless exciter works is that we add energy here. The brushless exciter will act as its own generator. Granted, it's completely inside out relative to the main generator, but it'll work just the same. So we add energy to the blue field coils on the brushless exciter. Internally, there are wires that go to the diode stack. The diode converts the alternating current into direct current, and then we have wires that lead back to the primary field. So again, this shaft has got holes drilled through it, and we're running wires through it. When you add energy to the brushless exciter, that energy is brought to the diode stack, where it's converted into direct current. That direct current then goes to the primary field windings, giving us that north, south, north, south that we needed for our 4-pole generator. Once again, the rotor is installed in the stator, where the length of these field coils are the same as the length of the stator coils. This mechanism is then bolted on such that it covers these components. This ring here is the stator for the brushless exciter. By adding energy to that, we can change the amount of energy that flows into the brushless exciter. That energy is converted from AC to DC in the diode stack. And when we're all done, the energy is then brought to the main field coils, establishing a north, south, north, south poles that we need to make this generator function. Before we leave, I'd like to take a quick look at the stator. This is a stator coil. You can see many coils wound on this stator. The output of the generator is taken from the stator. You can see that here in the outlet box, where we have thick, heavy wires leaving the generator. And that's a nice way to do it. Again, there's no contact between the rotating member and the stationary member. We mentioned this PMG, the permanent magnetic generator, and that has a rather interesting story to it. Because it turns out that it's not enough just to get a generator turning. Right? You would think that all you have to do is start the diesel engine or start the turbine and get the machine running and it would produce electricity. Wrong. In order for a synchronous machine, a synchronous generator to produce electricity, there has to be a strong magnetic field built up in the rotor. And the only way you're going to get that is if you have a source of energy from which to start the machine to begin with. One way to set this in motion is to use a PMG. And the way it works is the PMG will produce electricity as long as the machine is rotating. So the output of the PMG will go to the circuitry for the brushless exciter. So this machine drives this machine, and once that happens, then you have the primary field up and running again. The technical term for this is black start capability. Black in that there are no lights on in your factory and you need to bring up the generator. Understand that that's not a universal function, and some of our largest machines do not have this capability. In fact, some of our power plants won't even start unless they're already connected to a functioning power grid. It's only by taking energy from the power grid to turn on the generator that they can actually start producing electricity. Anyway, I thought you'd appreciate that. There's so much more we could talk about, but we better get back to the main point and talk about generators as part of a larger system. In particular, generators in parallel with other generators. Here's a diesel engine. Here's a generator. And here's the output of the generator, where power is, of course, equal to VI complex conjugate. The generator has a mechanism called an automatic voltage regulator, an AVR. The AVR will monitor the output of the generator, and it will control the brushless exciter, thereby providing the proper output voltage. Understand that there are two things that you can do to this generator. You can change the governor, which basically means you're changing the amount of fuel provided to the engine. The other control is the AVR, which means you're changing the field. That's it. Those are the only two things that you can do to this generator. You can change the fuel, which means you change the torque applied by the diesel engine, or you can change the field, which means the AVR is being adjusted to change the field in that main field coil. Hold those two thoughts. Hold those two thoughts because this is going to get really interesting. If we have a generator operating alone, if we have a generator, one generator, and it's operating all by itself, changing the fuel will change the real power, will ultimately change the frequency. I suppose that makes sense. If you put more fuel down the diesel engine, you can expect it to add more real power, and it should make the generator spin faster. If you adjust the AVR, you are adjusting the field current. By our equation, the internally generated voltage is equal to K phi omega. We can expect that the output voltage will change. Note that the power factor is determined by the load. This implies that the generator is not in control of the power factor. The generator will simply do whatever is necessary to maintain that power factor as demanded by the load. Again, that's a solitary generator powering a load. As we move to the next step, we need to learn a new term, and that is infinite bus. An infinite bus looks like this. Here is your generator. It is connected to a bus with many other generators. How many generators? Well, you could think of it as an infinite number of generators. Another way of saying that is that this generator is very small. It's very small compared to all of the other generators combined. Yet another way of saying that is that this generator is not able to change frequency or voltage. You could look at it this way. This generator has a circuit breaker. As soon as that circuit breaker was closed, this generator saw the bus as 480 volts. It saw the bus as 60 hertz because that's where all the other generators set it to. There is nothing you can do to this generator that will change those conditions. You can pour all the fuel you want down the throat of that diesel. It's not going to change the frequency. Likewise, you can put the AVR to max. It will not change the voltage. So if we come back here, we can talk about fuel. So adding fuel changes real power. And that's it. We don't change the frequency like we did when the generator is operating singly. All we do is we change the real power. Remember, there's only two things you can do. So we add fuel, or we can change the AVR, which means we're changing the field current. If we're changing the field current, all we're going to do is change the reactive power. Think about it this way. Here's the model of the generator. with the resistance of the winding and the reactance of the stator winding. These are the output terminals of the generator. If you took the output terminals of the generator and tied them directly to a source that was 277 volts at a phase angle of 0 degrees that was at 60 hertz forever, and then you came here and you started playing with this. Remember that the internally generated voltage is the function of K, phi, omega. You can't change K because that was already built into the machine. You can't change omega because we just said that we are always and forever locked to 60 hertz in this particular example. All you can do is change phi. So if you change the AVR, you're changing the field current, you're changing the field current, you're changing the voltage here. If you're changing that voltage, you're also changing the current. If we were to sketch this in the phasor domain, this is the terminal voltage. Remember, that's unchangeable. There's nothing a machine operating on an infinite bus can do to change that. It's fixed. We could adjust the machine so that the current has a phase angle of 0 degrees. If we do that, the internally generated voltage sits here. And since KVL must be satisfied, the voltage drop across those pieces is this vector like so. We could also adjust the current so that it sat here. If we did that, the internally generated voltage would shorten. It would look something like that. We could also adjust the generator the other way so that the current was lagging. If we did that, the internally generated voltage is now here. And that's what we mean by reactive power. So changing the AVR changes the magnetic field, changes the internally generated voltage of the machine, changes the current, which comes back and again changes reactive power. You can set reactive power to be whatever you want it to be. Actually, if you're at a power plant, you set it to whatever your ISO tells you to, and that is your assigned reactive power. Anyway, we looked at generators operating alone, generators operating on an infinite bus, and the last thing we want to look at is generators operating in island mode, which is to say you have two generators that are of similar size. To keep this simple, we'll just assume that there are two generators. Here's a circuit breaker, and here's the load that the generators are sharing. Our claim is that if you change the fuel, you will change both the frequency and real power balance between these two machines. You could think of it this way. You and I are riding a tandem bicycle. In the ideal situation, we're both pedaling with the same power and we're moving at the desired speed. If I get a little lazy, that means I'm consuming less fuel. What'll happen is that we slow down. The real power delivered to the load is reduced, and the frequency at which we're pedaling is reduced. Here's another way to look at it. If you're on that bicycle and you're pedaling all by yourself, you might have something that looks like this. As you, generator number 1, increase in power, right? As you increase in power, there will be a corresponding lowering of speed. So we're going to call this the frequency at which you're pedaling. And that would make sense. At no load, you can pedal pretty fast. At a much higher load, you're going to be slowed down. If we add me as generator number 2 power, which increases in this direction. By the way, this is a peculiar chart. It starts out with power here as 0, and it increases outward this way for both generators. My power might look something like this, which means I have a no-load speed that's lower because I don't like to pedal as fast, and I'm not quite as strong as you are, so the slope here is lower. So when I reach this much power, again, when I move out that far, I'm at this speed. At the same speed, you are here. By the way, we're on the same bicycle, aren't we? We're pedaling together, which means we are turning the same speed, and speed is equal to frequency. So this is how the power would balance out in reality, which means you can provide nearly twice the power that I can at that given speed. And speed is very important for balancing machines because the synchronous machines turn at the same speed as if you and I were riding that tandem bicycle. So if this was the characteristics of the real machines, right? If gen number 1 had a speed droop that looked like that, and gen number 2 had a speed droop that looked like this, well, that's what you get. They would balance out such that generator 1 would take twice the power of generator number 2. Notice we use the term similar in this example. Similar does not mean the same. Of course, if the machines were the same, this house diagram would be absolutely symmetrical. If we had more time, we could explore a similar house diagram for the reactive power. But for now, just realize this. If you are in island mode, which is to say you have multiple generators running together, and each generator is about the same size as every other generator, you need to balance voltage, you need to be mindful of frequency, you need to balance reactive power, and you need to balance the real power. That brings us full circle back to this switchboard, which we talked about on day number 1 of class. These are the things you need to balance. Each generator will have its own set of meters. Here's a frequency meter. In this case, you want to make sure that everything operates at 60 Hertz. There's a voltmeter right above it. Make sure your bus voltage is correct. In this particular case, it's 440 volts. Make sure your current and watt meters are equal, assuming the generators are equal size machines. If not, make sure they're operating within the limits of those particular machines. You'll be glad to know that there are controls to take care of all of this generator balancing for you. In fact, on this switchboard, lower down, there's a switch. Flip that switch into a mode called ISO, and it will take care of itself. It will automatically balance those two generators for you. While we're here, let's look at these synchronizing lamps and the synchroscope. We played with these in lab. We talked about phase sequence. If everything is good, the synchronizing lamps will come on and turn off at the same time. If you have the incorrect phase sequence, the synchronizing lamps will come on and off at different times. And you never want to close the breaker on generators if you have an incorrect phase sequence. To do so would destroy the generator. The synchroscope tells you the relative phase difference between the generators, right? You can say that this here would be in phase, and in phase for the synchroscope means pointing straight up. And then we can talk about the phases moving relative to each other, which is to say one generator is turning slightly faster or slightly slower relative to the other generator. Let's wrap this up by talking about the conditions for paralleling generators. If you're going to do it manually, you'll be standing in front of a switchboard that looks something like this. Make sure you're looking at the right switchboard, because often you'll have switchboards right next to each other, one for each generator. You want to make sure you're on the right switchboard. Make sure you're looking at the switchboard for the generator that is to be placed on the bus. When you do that, look at the voltages. Make sure your voltage for the oncoming generator is the same as the bus. Look at the phase sequence. Make sure your phase sequence is the same. There should be synchronizing lamps, right? All the lamps should be going on and off at the same time. Make sure the frequency of the oncoming generator is turning slightly faster than the bus, which means look at the synchroscope. You'll notice the synchroscope has two markings, one for slow and one for fast. You want to make sure the oncoming generator is turning the synchroscope in the fast direction. You'll want it to be moving in a clockwise direction. Maybe so it's making a revolution once every, say, 5 seconds or so. Okay, but make sure it's going in the fast direction. Now, the last thing we need to talk about is phase angle. Once again, we look to the synchroscope. You'll notice that there's a mark at the 12 o'clock position. That tells you that the phase angle of the oncoming generator matches the bus. But be careful. Earlier I said that the generator needs to be moving in the fast direction, making one revolution every, say, 3 to 5 seconds, which means the phases of the two generators are sliding relative to each other. You want to be very careful so that you close the bus only at the 12 o'clock position. So the generators are moving, they're moving, they're moving, close the breaker. And that way, the oncoming generator is in phase with the bus. Failure to do that, right? If you close the bus when they're out of sequence, you could destroy the actual generator. Let's write down those rules. We said same phase sequence, same voltage. The oncoming generator should be turning slightly faster than the bus, which means the synchroscope should be moving in a clockwise direction. If you fail to do this, your generator could trip the circuit breaker because of a reverse current condition. Not something you want to do. The final rule is close the circuit breaker when they have the same phase angle. That's this condition right here, where the synchroscope is slightly before the 12 o'clock position.